I don't think you're in danger of either.
Yeah, I don't think so.
Good morning, everybody. How was your weekend? Do you have any games?
Yeah.
How did it go? Okay. No need. Did you row over the weekend? Or did you tell people to row? I just broke my old sunglasses. I broke my new sunglasses over the weekend. Hence the old ones, which I just broke. I wanted to show you something kind of cool, but it requires you to see me do this cool thing, so pay attention. That's not good. If I hit this, it makes a tone that's kind of nice. We can do meditative things. I actually bought these from a meditating website. Interestingly enough, because they make a very pleasant tone. This is 256 hertz. This one is 440 hertz. It's very nice. What's going to happen to the tone if I put this little piece of plastic onto the end of the tine? Use your knowledge of physics or common sense and tell me what you think is going to happen. Say what? No noise at all? A dampened noise, meaning that it'll fade out faster. Same tone, but fading out faster. So this one makes the same noise. They're identical. And you think it's going to sound like that, it's just going to fade out faster. Not as loud. Okay, all right. Less amplitude. But the same frequency. As opposed to this one, which is a different frequency. You can hear that that's different, right? What do you think?
I think probably the tone's going to change, maybe.
You think the frequency will be different? Higher or lower?
Maybe lower.
Why do you think that?
Because isn't that like inhibiting its ability to move fast?
I mean, I guess I'm adding mass to it, right? What does mass do when you try to move something? What? Yeah, it adds to its blank. Newton's first law, the law of... Say it loud and proud, whoever said it. Somebody said it. Sam? Well, it is one of the three laws of motion, but specifically the first law is law of blank. No. Inertia. Conservation of energy is a law. It is not one of Newton's. That's I think, more general. Did you say sorry?
Yeah.
Don't be sorry. You answered. No one else was answering and you did. So don't be sorry. Be like, you're welcome.
You're welcome.
I appreciate it. Okay, so the law of inertia. By adding that piece of mass, maybe I add to its inertia, make it harder to move. So you think that would slow it down?
Yeah.
Because we know that there's a restorative force that makes it want to wobble back and forth, and it takes more force to move it if it has more mass. That seems reasonable too. All right, so who thinks it's going to have the same frequency but quieter? We'll call it the SAM theory. We got a couple. Your buddies support you back there. All right, who thinks it's going to have a lower frequency? It's the Amber theory. You didn't even raise your hand for your own theory.
I thought it was mine.
I don't support it. We have to practice self-care, right? Like we care about ourselves, support ourselves. Hey, but nobody else does, unfortunately. You guys, is that why you're sitting over like kind of alone? Because they don't support you? Jerks. Come on, people. Then you need a new theory, because I saw a bunch of people didn't vote. What's your theory?
So, okay, this might be far-fetched and I might be totally wrong.
Well, that's any guess.
Yeah. I think that because it's like on there, it's shortening the distance that like the waves have to go through, so it might make the frequency higher, so it might be.
Oh, okay, sort of like moving down the neck of the guitar. When I press the fret close,
Yes,
it's
I think
a
it
shorter
might be
string.
Higher pitch, but I think it's gonna be dampened, like, I don't think.
Okay.
Yeah.
So who thinks it's going to be higher pitched and dampened? The Kara theory. We got a couple supporters for the Kara theory. A few. But we still have a lot of people who are hesitant to vote. But everyone, what was it?
What did you say, no sound? Yeah, I said no sound.
Oh, I apologize. I totally forgot you said that. My bad. My bad. Who says no sound? Gaining popular support because I forgot it. All right, I apologize. My bad. My bad. All right, well, let's find out. Easy enough. I'm going to test it. I'm just going to slap it with the hammer and see what happens. Similar, but not quite the same. I'm going to make it a little bit more extreme. I'm going to move it down a little bit just to see if I can notice. By making it more extreme, make it more audibly available so I can hear it. Oh, those are really similar. I do know it's, in theory, supposed to change. But I truly don't actually remember if it makes it higher or lower. That was a real question. Well, those are different. I hear beats. Do you hear the beats? But they're too close for me to tell if it's higher or lower. So we'll have to do a little bit further research later. So I couldn't tell about the damping. I would guess that there is some. And my guess was that it would make it a lower pitch because of the inertia thing. But I honestly don't know the answer. That's something worth figuring out, worth looking up. And I do know that they're different. How do I know they're different? The beats. In fact, if we wanted to, we could measure the rate at which those beats occur and figure out exactly how different they are. You know how to do that. How, yeah.
I was just gonna say that it definitely sounds lower to me.
Okay. My ears aren't as good as your ears. That's just, it's a genetic thing. I don't hear so good. So I believe you. That being said, how could you figure out the difference in the frequency if we measured the beats? What's that relationship? We did it when we went over to the lab last class. Did everybody sign in? Anybody didn't sign in? Where you at? You tell me, I am not going to tell you the answer. There you go. The difference in the frequencies will equal the rate at which the beats occur. So if one is 440, which is known, this is definitely 440, and we know that the beats are occurring at 2 hertz. What would this one be? You have 2 options, both could be right. This one is 440, we know that. The beats are occurring at 2 hertz, 2 times per second. That, I don't know that that's actually what's happening, but that's a reasonable, it could be. What is the frequency of this one? It's either 438 or 442. If it's speeding up or slowing down, it's going to be 438 or 442. Make sense? Awesome. I want to show you something else that's kind of cool. Nothing, right? Damping. You ready for this? Still hear it, right? How come you still hear it? We didn't hear it before. How come you still hear it now? Say what? I still hear it. Ha! Why? It does pass on to the other one, that's for sure, because I can damp this one and then I damp this one and they both go away. I continue to hear it until I damp the second one. So I definitely know that the second one is vibrating, even though I didn't strike the second one. But why? Yeah, they're close together, that's true. But even when they were close together, when I put this on there, it didn't. Good theory. That's a good theory, that the stoppers may be pulling some of the energy out, but I'm going to give it a lot of energy. I'm going to hit it pretty hard. And that should be enough to overcome it. Ready? Still nothing. No sound at all coming from that one. So there's definitely enough energy. There's as much energy in the system when I whack it hard like that. So I don't think that's it. But that was a good guess. I like that, the thought process there. And I could also do a similar thing with this one. It doesn't really matter if it's facing one way or the other, but the sound comes out of this way, so it's a little easier to hear when it's not blocked up. And I do point the sound towards it with this one. Nothing. Definitely not affecting that one at all. Why? Say what? Yeah, I would say probably. I mean, what's the difference? That it worked when this wasn't on there. It didn't work when, or no. Yeah, it worked when it wasn't on there, it didn't work when it was. So this thing, we know, changed the frequency of the box. So the only difference was the frequency. So it must have something to do with the frequency of the two. When the frequency of the two is the same, it caused an oscillation without even touching it, just by being nearby. You know a name for this. I showed it with the mouse. If you add energy at the right frequency, the natural frequency for something, you get this effect. What is that effect? The worst you can be is wrong. That's a great guess, and it's related to that, but that's not the word I'm fishing for. But you're on the right track. So what? No.
Driven force?
No, it's not. So it's driven when I hit it, but after that, it's not. It starts with an R. So what? Resonance. It resonates. I asked you to look up the definition for resonance. I don't remember exactly who got it. Was it Sienna? Did you look up the definition of resonance for me?
Here.
Not the last class, but she was here when we talked about resonance. What is resonance?
Quality and sound of the people.
There's a second definition of it as well.
Reinforcement or control on each sound by reflection of the surface of a synchronous vibration.
A neighboring object, you say? A neighboring object like another tuning fork that has the same natural frequency? Resonance. So the resonant chamber on the bottom makes it louder, but you can resonate with things nearby as well. You cause it to oscillate because it shares that frequency. I don't know for a fact that this is true, but I think that is related to how they use tuning forks to find broken bones. So, kind of cool. Another example that I like to show of resonance is the Tacoma Narrows Bridge. Have you ever heard of this thing? It's pretty wild. I'm going to go on the internets and look up the Tacoma Narrows Bridge. This happened in apparently 1940. I thought it was in the 1950s, but it's the 1940s. And they caught it on video. So they built this big suspension bridge across the Tacoma Narrows.
Marcus is a connoisseur of...
This is a commercial. This is not part of the lesson.
He's happy to read the disclaimer on TurboTax Free Edition.
Oh, thank you.
This is really loud. Turn the volume down a little bit.
Bridge Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel.
There's wind going through the valley at the exact rate, the natural frequency for this bridge to resonate with that. And the oscillations in the bridge get reinforced by the wind coming through the valley, causing the oscillations to get bigger and bigger and bigger. And the damping, people are just like walking away. Like, that's wild to me. That's a cable that is 18 inches in diameter. Steel. And that's concrete. Totally freaky. He's just walking away. He's like, yep, That's normal.
Finally, the speed rose and the suspension cables give way and plunged into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Oh, apparently he did say that. That's unfortunate. I didn't actually know about the dog. That's news to me. But the Tacoma Narrows Bridge is a famous example of failed damping, essentially. They were unable to pull the energy out of the system to save the bridge. I asked an engineer friend now how they do that, and he just said they have mechanisms for damping. They have essentially shock systems in them. Like your car has shocks, the same kind of deal. Wild to think that that was concrete that was able to oscillate like that. And 18-inch steel cables, 18 inches in diameter is like over a foot, it's a foot and a half, right? Like that's a thick steel cable to be snapping like that. So it's a lot of energy. It's a lot of energy to be contained in the system. And it's all due to the resonance of the system. There's a similar thing that happened, but not quite as extreme, in I think 1999. In London, they built a bridge called the Millennium Bridge. I actually got to walk on the Millennium Bridge when I was in London. It was pretty cool. It's a footbridge to go over the river in London. And when they built it, they built damping up and down, but they didn't build any side-to-side damping. So the bridge started to sway a little bit side to side, and there was lots and lots of people on it. So when the bridge sways to the right, everybody leaned to the left, which made the bridge sway back to the left, which made everybody lean to the right, adding energy to the system, which at its natural frequency increased the amplitude of the oscillation and eventually caused the bridge to sort of make a snake S shape through the river. They had to close it and repair it over the course of a few years. And this was as recent as, like I said, 1999 and 2000. Thus the name Millennium Bridge. You can look it up. It's really interesting.
Very fun.
What?
Very fun.
Is it really? Oh, I didn't know that.
Last movie when the
Oh,
theory started causing shit in the real world.
Huh. I've actually never seen the last movie, so. I read the last book. I think I did the midnight opening in Barnes & Noble for buying the last book. So. All right. Awesome. Any questions about any of that stuff? I wanted to talk about resonance a little bit before we got into the next chapter, which is about sound. Sound is a specific type of wave. We're just going to kind of dig into the same details that we've been covering so far. It's a specific type of wave, and in the picture on the screen, we got an example of resonance. We've talked about it a little bit. You've seen probably on TV or in movies where the opera singer sings at the glass and the glass breaks. Why does that happen? Well, the glass, much like the bridge, and much like my tuning forks, have a natural frequency where they want to oscillate. When you add energy at that natural frequency, like we did with the tuning forks, we can pass on that oscillation to the object that's nearby. It can resonate with it. When that happens, the amplitude of the wave in the object increases. Remember, sound is a pressure wave, so we're adding pressure to the system, causing oscillations, in this case, in the glass. Eventually, the glass can't handle the level of amplitude of oscillation, and it shatters, like in the picture. I've never seen it in person, but I've seen plenty of videos of it. I'd like to see it in person. I don't know if I'd like to hear it in person, though. That might be uncomfortable. Plus, I don't have crystal glass money lying around. I work at a Catholic school. Maybe I'll use a physics budget and buy something. We'll go from there. I included this. It's out of the book. I just thought it was really funny. So it says a tree fell in the woods some time ago. The atoms of the air were disturbed. The disturbance, somebody could hear it, whether there's somebody there or not. Like, it made a sound. So yes, you do hear the tree fall in the woods, even if it makes a sound regardless of whether you're there to hear it or not. I thought that was funny. Apparently I'm the only one. That's okay, it doesn't matter, as long as it works for me, right? If a tree falls in the woods and nobody's there to hear it, does it make a sound? You've heard this before?
Yeah.
You've never heard that before? It's a famous saying, right?
I don't like understand, don't understand.
Okay, so I feel awkward having to explain this. No, it's not a joke. It's just like a famous, yeah. So if a tree falls in the woods and no one is there to hear it, does it actually make a sound? It makes you think about the reality of the world, right? Like, so a philosopher might ask you that question, but a physicist says, no, if the tree falls in the woods, of course it makes a sound because of physics. So
philosopher would say it doesn't make sense.
they say you couldn't possibly know because there's no one there to observe it. You've never heard,
I've heard it, but I've never understood it because obviously it would make a sound. So I've
well,
never-
you're a scientist, not a philosopher. Can you believe they'd never heard that before?
No, we
Wow.
we have.
No, you have. Amy hasn't.
Oh, I'm sorry.
And you're obviously a
Sorry, at this point.
well-educated, rounded individual. I'm just surprised you haven't heard that before. So, yeah, I don't know. That backfired, but interesting to know that you didn't hear that. Have you heard of that before? Okay, good. Did you understand it? Okay, all right. So I'm not alone.
My bad, sorry.
There's a big difference between, no, like, not knowing something isn't being stupid. It's just not knowing something. Being stupid is to not think about things, I think. But to just not understand it, that's not a big deal. Because now you do.
Yeah.
What's that?
I said that's good. I don't understand a lot of them.
Me too. Me too. Anybody who says that they do, probably lying to you. Or they haven't thought about it enough. Okay, so sound is a wave. It's a compression wave. It's made generally by oscillating objects that cause compression in the air molecules around them. Sound itself is the compression and stretching of the air molecules as they bounce back and forth. So in this case, we have a string that's oscillating back and forth. Or if you're thinking about the sound waves that I'm creating, if I put my hands on my neck like this and I talk to you, I can feel the vibrations. Try it. It's actually kind of fun. Say something to the people around you, you feel the vibrations.
How are you today?
Yeah? You feel it, right? Does that actually sound different when I put my hands here? If I'm talking like this or like this, I'm not changing the tone. Does it sound any different? No, no damping? Okay. I don't know. I was curious. But you can feel the vibrations, yeah? The vocal cords vibrate back and forth, causing air molecules to vibrate back and forth, which cause the air molecules next to them to vibrate back and forth, causing a longitudinal wave, or a compression wave, or a pressure wave. All of those are the same thing. In the case of sound, we have a wave of increasing pressure and decreasing pressure moving through space from me to you in this case, or from a speaker to you, or from a string to you, or from something that is oscillating back and forth causing this compression. The compression moves out at a known rate. When the string moves backwards, it's going to push air molecules together on this side. As this pressure wave moves forward, it's followed by a low pressure area. The high pressure area, as we've covered before, is called a compression. The low pressure area is called a rarefaction. If I made a graph of pressure versus time, it's going to be, if this is your normal atmospheric pressure, that is the baseline, that is the equilibrium. The sound wave is going to have high pressure, followed by low pressure, followed by high pressure, followed by low pressure. That compression wave goes from my vocal cords through space and hits your eardrum, which I don't remember the names of the stuff in there. You guys are biology students. You probably know the anatomy better than me. There's 4 bones, I think. Three? I know hammer and anvil are like the non-fancy names for those.
That's fair.
So your eardrum gets oscillated. It sends an electrical signal to your brain, which your brain interprets as sound, what you hear. There's a movie I like from the 70s, I think. It's called Alien, starring Sigourney Weaver. Have you ever heard of this movie before? Never heard of that movie before?
Nope.
I've never even heard.
John Hurt comes out. Oh my gosh, really?
Y'all should just start lying.
Well, I know it's older than me, so it's old, but it is also quite famous. It's like a quintessential sci-fi horror movie.
Not into that.
Anybody in the room heard of or seen the movie Alien? Raise them high, because okay, see? I'm not alone. Tell me a little bit about the movie Alien.
I've never seen it, so.
You've heard of it. Yeah, that's the one. The alien design is from a guy named H.R. Geiger. It's really scary. So in the movie, this has nothing to do with the lesson, but it's for your benefit because you should know these things. It's part of the zeitgeist of American culture. So in the movie, the spaceship comes to this deserted place, colony. They follow a distress signal or some such. They find a spaceship, and in that spaceship, they find a bunch of eggs. And they're looking around, and one of the eggs opens up, and out jumps this like monster that attaches to the dude's face. So when Joey was a baby, we used to play Alien, and there it is. So, and I would like walk my hand along and then go on his face, and he would laugh and giggle. It was a fun game based on a scary movie. But the alien would attach to their face, and they put an embryo in the guy, and the alien would come out. But the tagline for the movie, what was it? Look it up. You have it open. What was the tagline for that movie? This is actually back to the lesson. I needed to teach you about culture first, so you would understand. But now let's teach you about physics.
In space, no one can hear you scream.
You read it totally wrong. You have to read it like this. In space, no one can hear you scream. Try it again.
In space, no one can hear you scream.
That's so much better. That is so much better. Very much more dramatic.
Thank you.
Now that was about 3.5 minutes of our class time, which is a substantial proportion to just get you to say that tagline. Why would I do that? So a sound wave is carried by blank. And my clue to that answer is that the statement that she just read dramatically is true. Read it one more time.
In which way?
The good way, of course.
In space, no one can hear you scream.
You've got a future in this, I think. Dramatic
My
readings.
major to like
Drama.
drama.
So sound waves are carried by... In space, no one can hear you scream, so therefore it's not carrying the sound waves, is it? So what do you need? What do you not have when you're in space? What makes it so no one can hear you scream in space? You need air. You need something to compress. If you don't have air, you don't have pressure waves because there's nothing that's getting compressed. So in space, unless you have your own air with you, you can't hear. So when the Death Star exploded in Star Wars, and you have seen Star Wars, right?
Yes.
Okay, for goodness sakes. The Death Star, you wouldn't have heard it explode if you were on a spaceship somewhere else because there's nothing to carry the sound waves. You could see it because light waves carry their own medium with them. A light wave waving is an oscillating electric and magnetic field. So electric fields and magnetic fields permeate free space. You know that from what we've covered in this class so far. So since the fields are going through empty space, they can move through a vacuum. But sound waves, they can't. Sound waves need a medium to travel through. Specifically, in most cases when we're communicating, it's air. Sound waves can move through other stuff too. Like, you ever play the game when you go swimming in a swimming pool where you go underwater and try to say something and try to get the person next to you to figure out what you said to them? That's a fun game, right? You can hear them talk, but it's hard to understand. It's very garbled because our vocal cords aren't meant to work underwater. They're not designed that way. They're designed evolutionarily to work on land, in air. But sound does travel through water. In fact, it travels fast through water. It can also travel through materials. If I put my ear on the ground, I can hear something come, like you see we're making a lot of pop culture references today, but the old Western movies where they put their ear on the ground to hear the posse riding up at them, that's because sound can move through the ground too. It can move through lots of different mediums. It's a compression wave that goes through whatever might be carrying it, but it needs a medium to carry it. You can't get a compression wave to go through a vacuum. Thus, in space, no one can hear you scream.
Oh no, you can never do that.
That's my fallback career. Either if professor doesn't work, then motivational speaker or like voiceover actor.
Both good options.
Onward and upward. So we have a wave that is propagating. That means it's moving. Propagating waves, that just means they're going from point A to point B. We say propagate instead of just moving because they spread out. And this is important too. So my voice is fairly directional because of how my body is designed. I am sending my sound waves in general this way. But yes, I am speaking at Amber But you guys over here, you can still hear me, right? No, I didn't say listen, I said hear. I didn't say you're listening to me. Even if I face this way, you can still hear me. That's possibly due to echoing, but also because sound waves propagate out in three dimensions, 360 degrees all around me. If I have a light bulb right here, it's sending light waves out in all directions. Sound is a wave as well, and if I make a wave, it's going to propagate in all directions. That means that the energy that's being carried is also dissipating at a faster than you might expect rate, because it's spreading out. It's going this way, that way, that way, that way. The sphere that can hear me, that is feeling that pressure wave, is getting bigger and bigger and bigger as the radius gets bigger and bigger and bigger, which means the energy is getting spread out over the area of that sphere. And area increases at the rate of r squared, right? Always. Pi r squared or 4/3 pi r squared. The area gets bigger at a rate of r squared. So as r, the radius of that sphere, gets bigger, the energy that's being carried, the intensity of the wave, is reduced at a rate of 1/r squared. Make sense? Okay, cool. We'll get to the math of that a little bit later, but that's important to have in the back of your mind. This should look familiar. We talked about that last chapter. The relationship between wavelength and frequency is true for any wave that's propagating, and sound is a wave that propagates. So if we know the velocity of the sound wave and we know the frequency of the sound wave, we can figure out the wavelength. If we know the frequency and wavelengths, we can figure out how fast it's moving. If we know the wavelength and the velocity, we can figure out the frequency. It's just a relationship between those three things. This is 440 hertz. It's a nice tone, right? It's pleasant to hear. Some people were gritting their teeth when I was hitting it, but I don't know, that sounds nice to me. It rings out cleanly and purely, I think. We know exactly what frequency that is. If you could figure out the velocity of sound in this air that we are in right now, we could figure out the exact wavelength of that sound wave. And it's related to how much the tines of the fork wiggle. It's related to the temperature in the room. We're going to talk about all of those, actually probably some of those today. In fact, I think we talk about it on the next slide. So the velocity of the sound wave depends on a couple things. It depends on the medium through which it travels and the temperature of that medium. Here's a variety of different mediums through which it can move. This is right out of your textbook, so if you need it for your homework, you can look it up. At 0 degrees Celsius. So our baseline is 0. At 0 degrees Celsius, in air, so in cold air, 0 degrees Celsius, sound moves at 331 meters per second. That's a number you want to kind of commit to memory, because we use it in the equation on the bottom of this slide, which we'll get to in a second. In helium, less dense than air, sound moves really fast, with really interesting effects, actually. I was in there. It looks like I'm doing one of those. Do people still do that?
Yeah.
Do you?
Unfortunately.
Me too. Now we're cool like that. We're both cool together. Okay, so, why didn't it pop up? Okay, oh, there we go. So we have different velocities in different materials, different baseline velocities at 0 degrees, but also at any temperature. Those different densities of material give us different velocities of sound moving through them. And the effects of that on the sound that you hear are really interesting. And for some reason, this isn't showing up. There we go. Do you know Adam Savage from Mythbusters? He's awesome.
promise to show you something really cool as long as you promise not to try it at home, okay?
Go ahead and try it if you want to. I don't care.
Now, everyone wants to know why my voice sounds higher when I inhale helium.
My simple fact is that helium is 6 times less expeditious, means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that. And my voice gets really low, but I'm still funny. It's scientific!
If they had that up in the chemistry department, I'd really want to try that. I've never tried it before. Anybody have connections up in chemistry? Get us some sodium hexafluoride.
Every golf.
Yeah, but if I ask, they get suspicious.
Suspicious of who, yes?
Say we need it for a physics experiment.
Exactly, you could say that.
So let's go back a slide real quick. The frequency of oscillation of my vocal cords doesn't change, but the velocity changes, which is going to change the wavelength of the outcoming wave, which is going to change the frequency that you hear. So while the source has the same rate, the created wave that you produce doesn't, which is really, really interesting. So one thing it depends on is the material, the medium that it's moving through. The other thing that it depends on is the temperature through which, temperature of the medium through which it's moving. So not just what it's made out of, but also how warm or cold it is. So we have an equation for that. Velocity of the wave equals 331, which is our baseline velocity. This is for air, by the way. This is for air at sea level, but I think the elevation differences are fairly minimal. So for any of your computations, we're going to use this equation. Even though we're not quite sea level, we're actually pretty close. Erie is not very high above sea level. We're right by the lake. What is the elevation of Erie? Hey Siri, what's the elevation of Erie, Pennsylvania?
I found this on the web. What's that? Check it out.
What the?
728.
So only 728 feet, not too much. What's the elevation of Denver, Colorado? Somewhere around 5,280 because it's a mile-high city. Lubbock, Texas is somewhere around 3,000 feet, and New Mexico is even higher. New Mexico, when I was there, Santa Fe was like somewhere in the 4,000 to 5,000s. So we're pretty low in comparison to some places. So this equation will work for our calculation purposes. So the velocity of the wave at a different temperature is going to equal the velocity at 0 degrees times the ratio of temperatures raised to the 1/2 power, which is, what's the 1/2 power mean? The square root. So if I was to rewrite that, so it's not a 1/2 power. Velocity of the wave equals the velocity at 0 degrees, meters per second, times the square root of the temperature divided by 273 Kelvin. Now, this is important. This is very important when you're doing this. We need the inside of the square root term to be unitless. We need the units to cancel out. So since the bottom is 273 Kelvin, what does the top temperature have to be in?
Kelvin.
It's got to be in Kelvin. How do you get Kelvin? What if I gave you, hey Siri, what's the temperature right now?
Probably 54 degrees.
Okay, thanks Siri. Hey Siri, what's the temperature in Celsius right now?
It's 12 degrees right now.
It's 12 degrees Celsius. So I want to know what the velocity of sound is right now at 12 degrees Celsius. How do I get the Kelvin? Well, a Kelvin step in Kelvin temperature is the same as a degree Celsius. They are the same size steps, they just started at a different spot. 0 Kelvin is really, really cold. 12 degrees Celsius is a whole bunch of kelvins. 0 degrees Celsius is 273 Kelvin. So the steps are the same. So if 0 degrees Celsius, and it's off by a little, I think there's a 0.15 in there, but I don't think it's enough to affect our calculations. So if 0 degrees Celsius is 273 and we're at 12 degrees Celsius, what is 12 degrees Celsius in Kelvin? What is it?
285.
Yep. It's also just for your own, so you don't look foolish in front of other scientists, not degrees Kelvin, it's just Kelvin. 285 Kelvin. All right. So how fast does sound go in the air that we are currently occupying? So you plug your 285 in here, divide it, do the square root, multiply by 331, and one more time you got 0.15?
49.
Oh, 19. This is unitless, so that this is the only unit we have, meters per second, it works out. And that makes sense to me because at room temperature, which is about 20 degrees Celsius, 20 to 22 degrees Celsius, the speed of sound is 240 or 243. So it's a little colder than room temperature outside, so it's a little bit slower. Makes sense. Makes sense to you. I know it makes sense to me. Does it make sense to you? Nice. If I ask you to do that, you'd be able to? Yeah.
So what temperature would it like trigger you notice this
That's a good question. I don't know the answer to it. I don't know where it would sound different. I'm not sure. That's a great question, actually, because it's got several components. Because our ability to interpret sound is also different than, like, measurably different. So I can measure the difference between this and 331. That's noticeable by, like, measuring an instrument. But I don't know if our ears are sensitive enough to pick up on that. I really don't. It depends, because our ears work on a logarithmic scale, so we can have a really broad range of input. We can detect very, very quiet sounds and very, very loud sounds, but because that's how logarithmic scales work. But I don't know how sensitive it is to little changes. I don't know. Worth knowing, though, for sure. So when you learn that, and you can teach me, awesome. Uh-huh. Why is it frozen? It wasn't letting me advance to the next slide, so I had to close it and open it back up. PowerPoint. Ugh. Am I right? We use this for a lot of different purposes, actually, this known value for the speed of sound. Sonar works through bouncing sound off of stuff. Bats use it to track prey. If you have something moving at a known rate and you can figure out how long it takes to get to its destination, you can figure out how far away that destination is. If I'm moving at a known velocity and I travel a known distance, I can figure out how long it'll take. Similarly, if I'm traveling at a certain rate and I know how far away it is, I can figure out how long it'll take me to, that's the one I just did. If I know how long it took and I know how fast it's going, I can figure out how far away it is. That's the other one, yeah. That's what the bats are doing. They send out a tone, and instinctually they know how fast that's moving. And if they hear that tone come back to them, they can figure out how far away their prey object is, in this case a bug. I think dolphins do this too. And we do it. How does our, when you plug your motion detector in over in the lab, for Physics 1 lab, you plugged your motion detector in, turned it on, what did it do? What? Didn't it click? Click, 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 click. Sending out sound, collecting that sound. Kind of awesome. That's how it works. Oh, hey, a problem. I haven't solved this one yet, but I think I have the answer on here. So this isn't directly answering your question, but it's along the same lines. It says we have an audible range. We can hear frequencies as low as 20 hertz and as high as 20,000 hertz. Like I said, broad spectrum. That's why we have to use that logarithmic scale. So calculate the wavelengths at the ends of that spectrum. We don't have an equation that associates temperature, frequency, and wavelength, do we? So do we just give up? Sean, are you giving up?
No.
No, there's no quit in the sky. So what are we going to do? Sean, it seems hopeless. We don't have an equation.
Make one.
Yeah, you know, that's a good idea. What are we trying to find? Wavelengths. And we have frequency, and I know frequency and wavelength are related, but what's missing? No, we have temperature too. Say what? The velocity, because what's the equation that we have? What is the equation that we know? V equals F lambda, or lambda F, it's multiplication, it can go in any order, it doesn't matter. We know the frequencies, and we want the wavelength, so we need the velocity. Is there any way, any possibility of finding the velocity? Where might I look? Where might I look for an equation to find the velocity? Oh, there it is. I found it. Thanks. So we can find the velocity. That's not going to change regardless of the frequency input. So I'll find the velocity. It's going to be the same because the temperature is not changing. And then I'll plug in that velocity into this equation. I'll plug in the low range of the frequency, and we can find the wavelength at the low range. And then I'll plug in the high range and find the wavelength at the high range. I think you can do it. I have so much faith in you. I'm going to go sit in the back and let somebody else walk through the answer. But I'm going to give you a couple minutes to work. And that's probably all the time we're going to have. Probably. God, it never fully erases. Gives away the answer for the next class. Can you read that? I didn't bring any markers.
I have some.
Oh, actually, I know.
Yeah, but I'm gonna use it in the next class. So I don't want to steal your markers. Good enough.
Well, you can do it for this class and then erase it so they don't.
In the future. I'll bring markers next time. All right, did you get me an answer? No. We're gonna, I'm subbing in a ringer. The smartest person I know within arm's reach. You can do one or both, that's entirely up to you. So step one was to find the velocity, right? Oh, you did step one, you solved for wavelength. Good job. I'm sorry, I stepped on your toes. You want to do the talking? So we know we need to find the velocity divided by the frequency. We use our velocity equation. We plug in the known temperature, which is 30 degrees Celsius. But 30 degrees Celsius is how many Kelvin? 303. So we plug that into our equation. It's going to give us a velocity of 349-ish, 348.7 meters per second. Perfect. Awesome. Take that, plug that into our newly derived lambda equation. somewhere around 150 something. I don't know. Yeah, good. 7. Yeah, I was trying to do the math in my head. You beat me to the punch because I divided by 2 and then I was going to divide by 10. But you're just faster than me. Then we do the same thing at 20,000. So is that going to be bigger or smaller than the one at 20? Way smaller. Much higher frequency is going to have a much smaller wavelength, right? What's the unit for wavelength? Say what? I couldn't hear you. Meters. Own that stuff. Come on. Don't say it quiet. Say it loud. How are the people in future generations on this video going to hear what you said if you say it too quiet? Awesome. All right, folks, that's all the time we got. Good work. I'll see you guys on Wednesday.